Hey everyone, Dr. Keith here. So today we're going to learn about Excel Solver and linear programming in Excel Solver. This is a very useful tool to help us optimize a variety of problems and values. So here in the chapter in My Educator, take a moment to look through it before we start this video. Briefly read it. There's not too much here. But when you're ready, come down here, download this material, and we're going to get started working through some problems. So here's the Excel file opened up. Let's enable editing. Now, depending on your instructor, you may cover the Goal Seek tool, which is also very useful and a form of optimization problem solving. However, I'm going to go straight to this worksheet right here, Donuts Prepared. So you have a donut shop. You're trying to decide, based on my demand, based on my labor available, what is the optimal number of donuts to make to maximize profit? So there's a few things to keep in mind. These are terms back here from the chapter that, again, may be worth taking a look at. For each one of these problems, there is some objective function. We're usually trying to maximize or minimize something. Then we have decision variables and constraints. These are the three pieces involved in each of the linear programming models. So back here, our objective function is always represented by a cell that will have some Excel function in it. In this case, it's total profit, which is comprised of the sum product, meaning the sum of the amount of profit made for each donut times the number of donuts we're going to make, which will go in these cells here. So the objective function is always a single cell or a single value that has a formula in it. The next term, the decision variables, are the things that we need help deciding on. A better way to describe that is, in this case, it's the total number of donuts of each type. Donut holes, regular donuts, special donuts that we want to make. So we want Excel to help us come up with the optimal values for these decision variables to give us the highest possible profit. So thus far it's a lot like Goal Seek. The difference is, though, we also have what are called constraints. So we are constrained by the total number of labor values available. We're constrained by the cost to make donuts. We're constrained by demand. Actually, I want to take that back. The costs, I'm not going to call those a constraint because they're worked into the profit. Rather, we have total labor available as a constraint, and then the minimum and maximum demand is a constraint. Also, another constraint is that we can't make partial donuts. We have to make entire donuts, not pieces of donuts. So, Solver is a tool that helps us take each of these three components of a linear programming model, objective function, decision variables, and constraints all together, and will give us, help us make a decision about these variables. So let's go through a problem. If you don't already have this, click on Data. There's going to be a tool called Solver. So if you don't have Solver, like I don't right now, actually let me make this Excel fit the screen better. All right, there. What you need to do is come here to File, go down to Options, click on Add-ins. After Add-ins, go to Excel Add-ins, go. And right here, we need to include the Solver add-in. Now, in the next chapter, or in My Educator, we're going to be using this analysis tool pack. So if you want to go ahead and add that now, feel free to go ahead and put that on as well. Don't worry about either of these other options or any other options you might have as well. So hit OK. Give it a moment. Pretty soon you'll see, there we go, a new sort of area here on the ribbon, Solver and Data Analysis. So if that didn't work, I want you to pause this video, close Excel out, and try to add it in the exact same way again and restart it. Sometimes that'll make it appear. Alright, so let's open Solver. And here we have the three components. We have the objective function. What this is, it's going to refer to a particular cell that we want to be maximized, minimized, or set to a certain value. It's always going to be one cell, and it's always going to have a formula in it already. So those are some just key pieces of information to remember to help you as you're trying to work through Solver problems. So in this case, profit, it had a function in it already, sum product. We're going to say this is a cell that we want to maximize. If this was something like shipping costs or something else like that, we might want to minimize that. But in this case, we want to max. By changing variable cells, these are the decision variables. These are the cells we want Solver to help us set to the appropriate values. This is important. These cells will never have functions in them. So I'm going to hit close for now, just so you can see these cells currently have nothing in them. However, these cells are referenced. Over here in the profit per donut, this is going to be, whoops, that's not what I want. No, right here in profit. Okay? The sum product function says our total profit is the profit per donut times the number of donuts of each type made, all added up. So again, the decision variables will never have a function in it, but it will be referenced in the objective function. All right, back to Solver here. Still have that set. By changing variable cells, I'm going to click and drag all three of those. Those are the cells we want help. Now, if it helps you, feel free to put something in here. 10 of that type, 10 of that type, 10 of that type. So you see that your functions, it's a way of just testing to make sure that your functions are all working properly and that you're getting a profit. It doesn't matter if we put data in here as long as there's no functions in here. And the reason why is Excel is going to overwrite whatever's in our decision variable cells with whatever it thinks the most optimal values are. So that's why we don't want to have a function in there, is because it's going to get overridden. All right, by changing these cells, let's start by just solving this. Now, there's a few other things here. We're going to talk about subject to constraints in just a moment. We have different methods of solving a problem. Now, Excel is smart enough to go ahead and, if it can't use one solving method, it'll use a different one, and it tells you a little bit about the different options here. My suggestion is just to always start with Simple XLP and let Excel decide if it wants to change it or move it. Now, depending on your installation of Excel, I've noticed that some people have some different options set up. Let me show you what I have so you can just make sure. So I am going to deselect ignore integer constraints. I'll talk about that. I'll talk about why in just a minute. I'm going to leave everything else here the way they are. On GRG nonlinear, I think I'm going to leave all of that the way it is too. And I'm just going to hit OK. So if you don't have Excel, the newest version, I think I'm on 2015 here, or it's 2016, something like that. If you don't have this, you may see different options. Just do the best you can to match the options here with what you see on mine. You may have to get my version if you end up getting something different from me. Anyway, I'm going to hit OK, and I'm just going to solve. So I get this warning that appeared down here. Let me pull it up. It says the objective cell values do not converge. So as your instructor might have explained, think of Solver as a way of plotting a graph or plotting a curve and then finding the max or the minimum on the curve. So Excel plugs in a bunch of different values until it finds the location on the curve that is maximized or minimized. If the formula you've created by giving it this objective function and these decision variables is not a curve and does not have a max or a min, then this is going to happen. It's going to say the objective cell values do not converge. So I'm just going to hit OK, and it's going to keep the last thing I put into Solver. OK, not a problem. Let me open Solver back up again. Let's start adding some constraints. So first of all, let's take a look. Let me close this. Let's take a look at our information down here. It says maximize profit by changing how many of each donut you make. You must meet minimum demand to keep customers happy. Now, this is not always true. Okay, it says you've got to meet minimum demand, but must not exceed maximum demand, or else you'll lose money on inventory. You won't always get a minimum and a maximum demand. Where did these numbers come from in the first place? Well, someone had to do some research and look at some actual data and plug that in there. Sometimes you might just get one number called demand. Here's the demand for each type, and then you've got to decide, do I want to make at least that many or only up to that many? And you'll find that Solver will often determine for you whether you're going to meet demand or not. I'll show you what I mean a little bit later here. So for now, we know that we need to make at least this many and no more than that many. So let's add that now as a constraint in Solver. So here where it says subject to constraints, I'm going to click add, and it says, all right, reference some cells, not a problem. I'm going to say that the total donuts made is going to be greater than or equal to minimum demand. I'm going to add this. Now, by adding that, see how it clears out my cells? What it did, I'm going to hit OK. Oh, whoops. I'm going to hit cancel. Notice it added that constraint right here to the list. So now let's add another one. I'm going to say that the amount made also has to be less than or equal to, click over here, maximum demand. Okay. So now I have these two. The first one says amount made is less than or equal to minimum, greater than or equal to maximum. Let's hit solve. Okay, solver, this time it says solver found a solution. All constraints and conditions are satisfied. Do you want to keep the solver solution? Yes. I'm just going to hit OK. And it says, all right, here's what we recommend. Make 250 holes, 200 regular, and 150 special. That basically, we're meeting maximum demand. All right, take a look at this spreadsheet. Is there any problem with that, or have we found the right solution? Well, I want to do a couple things. First of all, I want to make sure there that I can see decimal places. So I don't have any partial donuts. It says whole units only, so that I'm okay there. Let's see, any other problems? How about this right here? I've used 25.5 hours of labor, but I only had 20 available. Okay. That's not going to work. I need to add another constraint to make sure that this doesn't get violated. All right. Well, go back to data, open solver. Let's add another constraint. This time we're going to say that this cell right here, total labor used, has to be less than or equal to total labor available. Okay. Now that constraint's added right here. Let's hit solve. Solver found a solution. It's happy. We hit OK. Now it says, all right, well, given that we can't use any more than 20 hours, then in that case, we recommend that you make the maximum amount of special donuts possible, 130 of the regulars, and 150 of the wholes. Okay, let's try and guess as to how it came up with that solution. Well, profit per donut's greatest with the special, so that makes sense. It's going to make as many of those as possible. But why is it making only 130 of the regular, since that's the next highest profit? Why not make all 200 of those? Well, remember, another one of the constraints was we can't make any less than minimum demand. So wholes, where we make the least amount of profit, it met only minimum demand. However, after hitting the max of special and the minimum of wholes, the only amount of the labor remaining only allowed us to make 130 of the regular. So based on profit, you can see how it came up with this optimal solution. Total profit is 120. Now it says whole units only. It didn't try to make any partial units, so that wasn't a problem in this case. However, if for some reason it did try to make a partial donut, we have a way of solving that problem. Come back to solver. Here under add constraint, we're going to say these cells, number made, must be integers, int. We don't put cells over here. We just say these cells have got to be integers. We hit OK. We know that it didn't try to use decimals before, so it's not going to change our solution. Still 120. All is good. Okay, let's move on to the next one here. Let's go over to shipping. In this case, we're in charge of shipping for a large multinational firm. We want to figure out the least expensive way to ship goods from your ports, which are in these cities. So we have 3 ports. And we want to ship to the following 6 warehouses. We must meet demand without excess. Okay, so here it gave us a clue. You won't always know that you've got to meet demand without excess. It may simply say demand. Well, here's number needed at each place. So meeting without excess means that we should make the total number shipped right here less than or equal to the total number needed. So unlike the previous problem where we had a max and min demand, we just had number needed here, and we don't want to exceed it. In other cases, we may be told that you don't want to make any less than demand, because demand sometimes is just a guess. And it could be that we've decided the profit from exceeding demand is worth the risk that we might make more than is needed. It's more valuable to do that than to suffer the costs of making more than is needed. So every problem is different, that's my point. But for this one, it tells us, don't make any more than this number right here. Okay? So you can't have negative inventory. That makes sense. Let's look down here. So it looks like we have this starting inventory for each port, number remaining, so we can't let these numbers go below 0. Number shipped must not be less than the number needed. Okay, it just says you must meet demand without excess, but the number shipped must not be less than the number needed. So basically, we have to ship exactly this number. So the point, if these are the shipping costs right here from each of these 3 locations to those 6 locations, then we want to decide, okay, where should we ship things from to get them to these locations to meet that demand and minimize shipping costs. So here's my total shipping costs for shipping from each location, overall total. These numbers right here, these 25s, are just some example data that are thrown in here to show you that all of the, to show you that all of the formulas are working. So see, we've got here a sum of the total number shipped. If we were to ship this many from each of these locations, here's total number needed. Anyway, let's go ahead and set up our problem. So, solver, set objective. What's the objective in this problem? What are we trying to accomplish? Well, remember the rules. The objective function in Excel is always going to be a single value or a single cell that needs to be maximized or minimized, and there must be a formula already or a function in that cell. In this case, as you can probably guess, we want to minimize shipping costs, and there is a formula in here based on summing up the shipping totals from each individual location. So that looks good. Back to solver. Let's click on G25. We want to minimize it. This is the part that's confusing often. The decision variables. Which cells do we want Excel to help us out with? Do we want Excel to determine the values for? Again, remember the rules. In this case, the decision variables should not have should not have formulas in them, but rather these are cells that are going to be changed by Excel. So the mistake a lot of people make on this problem is they say, well, right here, number to be shipped. We want to have it change how many are shipped to match and equal this. Well, no, not exactly. Remember, this is the sum of total shipping from all 3 locations. Denver needs 150, but Denver doesn't care where they come from. They just need 150. But we want to make sure we send them from the cheapest possible places. All right, so what we want is Excel to help us change the individual number of items shipped from each location to each location. All this is a validity check. It's a way to sum it up and check and make sure that total number shipped is going to equal the number needed. All right, so back here in solver, by changing variable cells, it's all of these right here, D13 to F18. All right, let's try and go ahead and solve that without any constraints. Solver found a solution. All constraints and optimality, an interesting word, optimality conditions are satisfied. Great, cool. And its decision was to ship absolutely nothing. Well, that makes sense. That's going to minimize shipping costs. However, we do have some constraints. For example, we have to at least ship this number and no more than that number. So let's add that one in next. So solver, add. What's one way to do that, to make sure that total shipped is at least this number and no more than this number? Well, this is why we added this column over here to make life a bit easier. We could say sum up all of these and make sure that they equal all of those. But since they're already summed up over here, we're simply going to say these cells must equal these cells. Okay. All right, let's solve that one now. All right, once again, it found a solution. It wants to ship almost everything from St. Louis. That seems to be the most central location, therefore it's cheapest to ship from the most central place. That makes sense. Other than LA to Seattle, Los Angeles is closer to Seattle than St. Louis is, so that makes sense that it wants to ship those from there. Are there any problems with this? We'll take a look through the results. We started with this amount of inventory, and now we have negative in this location. Okay. In that case, we're going to have to adjust this. Add another constraint. Oops, not data analysis. Let's open up Solver again. Let's add another constraint. What should it be? Let's say that these numbers must be less than or equal to, no, that doesn't make sense, greater than or equal to 0. That's one way of making sure that none of these are ever negative. Let's hit OK. Solve that one. Solver found a solution. It's happy. Let's hit OK. Alright, so we've got something a little funky that's happened here. Negative 5e to the negative 06. What does that mean? Well, this is scientific notation. Basically means that we have some decimals in here. We fixed this problem where we're now ending with we no longer have a negative inventory, but we can't ship partial packages. Alright, that should be fairly obvious. Even though it doesn't say it in here, I can't ship point whatever that is. So we need to add another constraint, just like we did last time. This time the integer constraint matters. We're going to say all of these cells must be integers. Okay, solve that. Found a solution. It's happy. There we go. Now, no decimals. Shipping costs $56,690. We've got nothing here that is below 0. This seems to be a pretty happy solution. Alright, let's move on and try another one. Transistors. This one is interesting. So we have a manufacturing plant, transistor manufacturing plant with 4 technicians represented by these letters, Tech A, B, C, and D. They make 3 different products. The demand for the products is shown below. Okay, let's take a look. Here we go. Here's the demand for each product. Here's the total made based on different techs making different products. But we have another problem here. Technician A can only make products 1 and 3. Technician B can only make 1 and 2, and C can only make 3, D can only make 2. So we have this table that says here's the number of hours required for each technician to make each product. And here's the amount of profit we make on each product. So we want to maximize profit while not using more than the available hours, and also not allowing any technicians to make any units or products that they don't know how to make. Alright, let's solve this problem. Oops, this one, oh, looks like we already left the answer in here. Good for us. Let's reset everything. I'm going to close this, and let's also change all of these to 1s so we can start over. Alright, so already this violates our constraints because Tech A can't make product 2. However, we're going to set this problem up and fix that right now. However, notice that total hours worked here, this sum product function seems to work nicely. If Tech A makes 1 of 1 and 1 of 3, well, it takes them 2 hours for product 1 and 3 hours for product 3. They worked a total of 5 hours. So our total hours worked function seems to be working just fine here. Let's go to Solver. Alright, set objective. What's our objective? Well, our objective is to maximize profit. So we want to make sure we click on a cell that has a formula in it and that we've correctly maximized or minimized it or set it to a value. By changing variable cells, alright, what do we want to change? Is it this table? No, this is our lookup table that says how many hours are required for each technician for each product. Is it the number of products made? No, because our decision variable cells should never have a function in them, and these cells have functions. It's summing up total units made by tech. We want to edit these cells right here, and that will that's what will determine how many products are made. So let's go ahead and hit solve. Objective cell values do not converge. Okay, so we know we need at least some constraints in there to come up with some type of value. Alright, let's try again. Solver. We know that we need to make, does it tell us at least demand or more than demand? It just says the demand is shown below. Perfect. This is an example of what I'm talking about, where sometimes we're given demand. And does that mean we should set it greater than or equal to that demand or less than or equal to that demand? you don't always know. So what I want you to do, and it's about time you learn this technique, it's very important that you learn how to do things one step at a time. Notice I've been adding in constraints one step at a time and then trying to solve it after each constraint. That's a great way to debug and make sure you find out exactly where you have problems. One of the biggest mistakes I see students make is they think through all the constraints, they throw all of them in there, they try and run it, and it doesn't work. And then they have no idea, well, why isn't it working? Then on an exam, they sit there staring at it for way too long, losing time trying to figure it out. But if you try and solve after every step, you'll actually be done a lot quicker and find out where your problems are. So let's open Solver up and let's experiment. Let's add a constraint and say that the products made must be less than or equal to demand. All right, let's add that one and see if it works. Solver found a solution. It's happy. It is less than or equal to demand. It made it as high as it could because we told it we're trying to maximize profit. Well, what it wants is for Technician A to make all products because Technician A seems to be the fastest at each product. Now, in this case, 50, Technician A can't make that product. So we violated that. Also, Technician A can't work more than 120 hours. We violated that constraint. So let's add a few more constraints in. Solver, add, let's say that hours worked must be less than or equal to hours available. And start with that one. Okay, solve, found a solution. Okay, so now it's spreading the love out a little bit. The problem we have still, though, is that it has various technicians making products that they're not able to make. Like this one, this one, this one. All right, well, we can fix that. How do we do it? See if you can pause the video right now and figure out how to do that. It's always best if you can do these things on your own. All right, if you couldn't do it, no problem. Let's do it together right now. So the next step is to add a constraint that doesn't allow Technician A to make any of product 2. So I'm going to say this cell right here, D14, must be equal to 0. That's it. Hit OK, solve it. Found a solution. So what did it do? It said, fine, we'll keep that at 0, and we'll put it over here on Tech C. Well, wait a minute, Tech C also can't make it. So we're going to have to go through and do this for every one of those cells. It's not that bad. Open Solver back up, say add. Let's just go through each one of these. Tech B can't make product 3. So let's set E15 equal to 0, add. Tech C can't make 1 or 2, so let's set these two equal to 0, add. No, and if you're wondering, there's not a way to add all of them at once. I can only add contiguous cells and not I can't hold down Control, for example, and add each of them. Lastly, Tech D can't make A and can't make 1 and can't make 3. Okay, let's solve that one. All right, let's check. So Tech A, they're not making product 2, good. Tech B, in this case, they're not making 2 or 3. Now, that may not be because we may have put in an incorrect constraint setting that one equal to 0, but it may not be. It may simply be that it's cheaper to have someone else make that product altogether. So we'll double check that. Tech C is not making 1 or 2 good, and Tech D is not making 1 or 3 good. Here's a problem though. Again, transistors, you can't make 0.2857 of a transistor. So let's go in here and let's add another integer constraint and say none of these cells, or all of those cells, must be integers. Hit OK, solve, found a solution. All right, it's happy. The only thing I want to do now before we finish and call this the right solution, I want to double check and make sure for some reason it wants Tech B to not make any of product 2, even though Tech B is faster at product 2 than Tech D is. So let's check and make sure I haven't accidentally put an additional constraint setting this cell to 0 that shouldn't be 0. So come to Solver, and what I'm checking to see is if E14 has been forced to 0 anywhere. There's E15. Nope, not E14. So basically they've decided that Tech B, it'd be better to have Tech B spend all of his or her time making product 1, even though she or he is the fastest at product B. It's better to have someone else make that product. Not a problem. Let's close this, and we're happy now with that solution. Okay, moving on. Candy bars. So here we've got a company that makes these 4 candy bars, and here's the ingredients. This is basically the recipe for each candy bar. Here's the cost to make based on those ingredients. Here's total demand, and again, we don't know if we want to make less than or equal to or greater than that demand. Total made, this is just some dummy data thrown in there. This is probably what we're going to want Excel to change and help us determine how many of each of these should we make based on the amount of profit we get per bar and the amount of ingredients available. So let's open up Solver. Now somewhere we better find our objective function. Oh, right here, total profit. We're wanting to maximize total profit, the sum of the profit of each bar. This is simply the total number of each bar multiplied by the profit per bar right here. Okay, no problem. Open up Solver. We want to maximize profit. Good, set to a max. By changing, well, we can't change the ingredients. We can't change demand. We can't change profit. We can't change the amount available. All we can change is how many that we want to make. So this is what we want Excel to help us determine. And once again, don't forget, the objective function is a cell that always has a formula in it, which this cell does. And by changing variable cells or decision variables, these will never have a formula or function in it because Excel is going to change the value of these cells for us. All right, let's hit solve. Excel, the objective values do not converge. In this case, it kept adding more and more and more made, and there was nothing to stop it to try and maximize profit. These numbers, it's just not big enough to show the numbers in the cells. There we go. And eventually, it stops after a certain number of iterations, and then just sort of gives up and says, look, we've got nothing to constrain us. So let's add some constraints. The biggest one, first of all, is that we're not going to ever make or be able to sell this many. If demand's only 1,000 for each, we clearly can't make that many. So let's add a constraint that says total made must be less than or equal to demand. Okay, let's solve that. Hooray, found a solution. Okay, so it says, cool, make 1,000 of each. And because the more you make, the more profit you make. And if you don't want to make any more than 1,000, then just go ahead and make that max 1,000 for each of them. But if you look down here, you'll notice that creates a problem. We don't have that many materials. We only have 2,500 units, whatever that is, of each of these ingredients. So let's add another constraint that says total used must be less than or equal to available. Okay, solve that one. There we go. Found a solution. So in this case, it says, fine, make 0 Snickers, 500 nut rolls, and 1,000 of each of these. Total profit, $12.50. All right, any of these constraints violated? Nope, that looks good. Nothing to do with labor or making less than demand. That looks pretty good. Okay, I think we've got one left here, staffing. All right, let's, on this one, I think we've once again left in the correct solution. So let us, oh no, we haven't. Never mind, sorry. Let's make sure the solver's cleared. It is, there we go. So here's our issue. All right, we're in charge of staffing the people needed for a large airline. When I call an employee to come in and work, they're going to work for 5 days straight and then go home for 2 days. So they have sort of this variable schedule where if I call them in on a Sunday, they're going to work Sunday through Thursday, have Friday and Saturday off. If I call them in on Wednesday, they're going to work Wednesday, Thursday, Friday, Saturday, Sunday, and then have Monday and Tuesday off. So what I have here is total number of staff needed. Then staff scheduled for each day is going to be the sum of the day of the staff called in that day plus the previous 5 days, right? Because if I call someone in on Wednesday, they're still going to be there on Sunday. So I can count on those 25 people still being there. Plus the people that I called in on Thursday, Friday, Saturday are also all going to be there. So 125 is a running total of the people called in on that day and the previous 4 days. So what I need to do is make sure that I have as little excess staff possible while making sure that I have or meet the minimum staff required. So here's an example of where we're doing the opposite. Instead of trying to get less than or equal to demand, I need equal to or greater than demand. So here's my total staff needed. Whole people only, meaning I can't call in 0.5 of someone to help work. I've got to set that integer constraint. So this is actually not as hard as it might look. Let's go ahead and set our objective function. In this case, total staff needed, we want to minimize. I want, as few people as possible to come in so I don't have to pay them as much, or don't have as high of a labor cost. By changing variable cells, so what do we change? Again, if you're ever unsure about this, go through the problem and find out, okay, which cells don't have functions in them. Those are the ones that I can use for my decision variables. Staff needed doesn't have a function in it, but do I want Excel to change the amount needed? No, this is demand. This comes from somewhere else. I don't want Excel to change this. Because I can't change what demand is. All I can change is the number of people I call in each day. That's what I want Excel to help me with. How many people should I call in each day of the week to meet that demand, or to meet the staff needed? All right, no problem. By changing variable cells, that's these right here. So excess staff just tells me the difference between total staff needed and total staff scheduled. In this case, I'm saying that excess staff, I have 65 extra because I have 125 scheduled and only 60 needed. Here I have negative 17 excess, meaning I'm short 17 people. Alright, let's go ahead and solve this without any constraints. It did find a solution. It says don't bring in anybody on any day, and that will minimize total staff needed. Well, duh, right? The problem is we need to meet this amount. So in other words, we need to make sure that excess staff is always greater than or equal to 0. No problem. Let's go to solver. Let's add that constraint. Excess staff should be not less than, but greater than or equal to 0. Add that, solve. Okay, cool, here we go. The best it could do is, as long as I invite 1.1 2/3 of a person this day, 108 2/3 of a person this day, and so forth, the only day I'll ever have excess staff is on Saturday when I have 81 1/3 people. Well, clearly that's a problem. I can't have partial people scheduled, so let's fix the integer constraint. Add number of people starting each day has to be an integer. Okay. Solve. Okay. Alright, here we go. Number of people starting on each day. 1 starts Sunday, 108 start Monday, and then I have 0 excess, except for again on Saturday. I have 18 excess people. Now, this was an easy one. Yours might actually be different. When I've done this particular problem with students, I've actually had some people get 18 on Sunday or on a different day. Well, this is a situation where there's actually a line scheduled, or not scheduled. There's a relationship plotted on a graph, or a curve drawn, that has 2 maximum points that are at the exact same point. So imagine a curve that goes up and peaks and then goes down, and then goes up and peaks again at the exact same spot and then goes down. So there's 2 peaks on the curve. As long as both of the peaks, or in this case it's actually a minimum, it goes down and then hits a minimum and goes up, then it goes down, hits a minimum and goes up again. As long as those 2 minimums are at the exact same point, meaning that I'll only have 18 people excess, does it matter which one I use? Not at all. Or if it does, there might be some other criteria I'll use to pick one of those 2. But unfortunately, Excel Solver doesn't tell us, hey, there's more than one optimal solution. It just seemingly a random gives us one of the 2. Okay, that's it for Solver. My suggestion for you is, now that you've gone through this video, start this whole worksheet over again, close it without saving, or open up a new one, and see if you can do all of these problems without watching this video or without any help. Anyway, good luck with Solver in the future.